Today I will teach about UART programming, about receiving the data, and then we will send it to another device, okay, using the UART. So let's write the code. This is just including that std in library, and this library can mainly focus on the width of the integers data type, like 8-bit, 16-bit, 32-bit, 64-bit, etc. And the code we are writing about Java microcontroller that on Cortex M4 base use many kind of integers. Use many integers, and they are 32-bit integers type. So there are 32-bit types, but their values are zeros and 1. So we will use this the 32-bit integers data types, because whatever we want to set, we are going to set it to 1 in the forms of integers. In the in using all those bits of that integers. This is just including the library of the Java microcontroller. This is just sending of data through UART data transmission process. Let me explain this code a little bit later with the flow of the code. This is the receive code, receiving the data using UART data transmission process. Let me explain this code a little bit later with the flow of the code. Okay. This is the delay code. Let me explain this code with the flow of the code. Okay. Don't mind. It will be more easy if I explain it with the flow of the code. This is the main code. We will come to this. Let's check where I will see. Here I will use port E, so we'll write 1 in hexadecimal, 0 in hexadecimal is this. I mean this 1 in hexadecimal and this 0 in hexadecimal. Here again, the system control. The system control is now using the RCGC GPIO, and the values of RCGC GPIO is 0x10 and 1 in hexadecimal is this, and 0 in hexadecimal is this. Okay, this RCGC GPIO is the 32-bit resistors of Java microcontroller, and this resistor, this RCGC GPIO resistor says, this is wrong. This RCGC 1 in hexadecimal is this, right? So this RCGC GPIO says supply clock source to any one of the bit from bit 0 to bit 5 and choose a particular UART port or GPIO you want to use. Here, if you supply the clock source to bit zeros of this RCGC GPIO, then you have chosen the GPIO E or port E. If you supply the clock source to here, then you have chosen spot B or GPIO B. Here, I have supplied the clock source here, so I have chosen GPIO E or port E. Okay. This is very simple code. Okay. Here I will use UART 5. So I will use this. We are using UART 0 from in before code many times, so let's use another UART model 5. 2 in hexadecimal is here. This one 2 in hexadecimal is this, and 0 in hexadecimal is this. Okay, this line is just saying system control is now using RCGC UART, a 32-bit registers Optiva microcontroller and Cortex M4 base microcontroller, and this register RCGC UART value is 0x20. 2 in hexadecimal is 0010, and 0 in hexadecimal is this 0000. So this RCGC UART says supply a clock source to any one of the bit from bit 0 to bit 7 in order to choose a particular UART module you want to choose. If you supply the clock source to the bit zeros of this RCGC UART 32-bit resistor, if you supply the clock source to bit 0 of this resistor, then you have chosen the UART modules 0. If you supply the clock source to this bit 1, then you have chosen UART modules 1, and so on. I have supplied the clock source to the bit D5, so I have chosen UART modules 5, because UART modules start from 0. So let's initialize this UART modules 5. Here, this line is just saying UART module 5 is now using the control registers UART control register, and its values is equivalent to 0. This values is equivalent to 0 means all the bit of this UART control register, this control register will be 0 except those reserved one. Let me show you the resistor so that you become more familiar with the resistor. This is the UART control resistor. I have written CDL control only in our code. So this one is bit 0. Bit 0 is UART enables bit. So I have kept the values 0 everything. That means UART is disabled. If UART is disabled, everything is disabled. So this DXE bit, transmit enable bit. This transmit enables bit when set to 1, that is when it is on or when it is enabled, this bit is enabled, it transmit we can transmit data through the UART data transmission process. But we set it to 0 because here we put everything, the values of the bit equals to 0 except reserve 1 in our code. So TXE bit is not 0, so it's not working. RXE bit is also 0, it's not working. But the man is okay, we shall focus in this because this is UART enable. Here okay, we put 0, so UART is disabled. If UART is disabled, all the functions of UART, okay, all those bits that do okay functions of UART will not work if UART is disabled. So we will okay focus to this bit particularly. So we will say control equal to 0 means UART is disabled. UART is disabled. This is necessary because we want to set up everything, configure everything, and after that we want to enable UART. Let me explain that line with this line together because it represents only one thing. I mean it comes together. This line okay need to be explained together with this line because these two lines represent only one thing. So let me explain this two line here. Okay, listen carefully. The baud rate. The baud rate is defined as the speed at which bits or data or a stream of bit or bit by bit is a flow, or it's again the speed at which again they are transferred in the UART data transmission process. Okay, I will explain it again. Baud rate is defined as the speed at which data or bit stream or bit by bit or bytes they are transfer at they are transferred in our UART data transmission process. The speed at which they are flowing or they are being transferred or they are being sent in the UART data transmission process. Okay, so this baud rate can be calculated using the following formula, and the formula is desired baud rate equal to system clock by 16 multiplied by clock tip. This is multiplication symbol, okay, not underscore. Remember, this is multiplication symbol. The system clock has a default value of 16 megahertz. Okay, the default system clock value is 16 megahertz. So we will put this 16 megahertz in the system clock. Then this line become this line. I just put 16 megahertz replacing system clock. That's it. Since this is multiplication symbol, we can cancel the 16s, and this 16 and this 16 we can cancel as this is multiplication symbol and not underscore. So we can cancel this 16 and this 16. Then we get 1 megahertz by clock tip. This one, 1 megahertz by clock tip. I will put the values of the clock tip 9600. In these equations, look carefully, this is megahertz. Megahertz is a higher unit of frequency and it is just a unit, so we will not count. The man-term left is 1 is also we will not count. Okay, the only man-term left is 9600. This equation is often from this equation. This expression is often from this expression. So this expression, okay, is the right hand side of the equations. This is the left hand side of the equations. In the left hand side, it says the baud rate. This is the only value left, or the term left in this expression. This is demand, okay. This is demand value. So this becomes the value of the baud rate. Okay. So the baud rate. So the baud rate in the left hand side equals to value of the baud rate 9600. And also, okay, if you know that frequency is usually expressed by 1V. V means the value. Yeah. Okay, fine. That's it. This megahertz, listen carefully, I'm going to say another again. This megahertz is a higher unit of frequency. Okay, in mathematical expression, we can reduce it to standard unit of frequency, and this is very common in mathematical calculations or any kind of physics calculations or electronics calculations. So we will reduce this higher unit of frequency megahertz to standard unit of frequency hertz, and 1 megahertz equal to 1000 hertz. So this megahertz we will convert to 1000 hertz. Okay, and divided by 9600, here also 9600. This term 1000 thousands by 9600, same I copy here, 1000 by 9600. What does this expression means? What is the meaning of this expression? The expression of this the meaning of this expression is sending 1000 bits at a baud rate value of 9600. Okay, so let's consider only sending 1 bits at a baud rate value of 9600. So here we have sending only 1 bits and a baud rate value of 9600. It says that 9600 is the balance of the baud rate. That means the baud rate. So what does this mean? The 9600, the baud rate. What is the meaning of that? The 9600 is the values of the baud rate. The real meaning of that is signal changes 9600 times per second. In 1 second, signal changes 9600 times. Signal means, I believe everybody knows that in a graph. Okay, I know. Okay, everybody study maths in arts and science and commerce also. So in the maths, in geometry portions, there is a graph. You draw it, and that sine wave, cosine wave, and all those things. So that full signal means starting from 0, then reach the highest peak, then amplitude, the highest value of the amplitude, and then reach the 0 again, then again goes to the lowest, the negative negative highest value of the amplitude, and then coming back to the 0 again, to the baseline, to the 0 line. So that's complete one cycle, full cycle. That is signal. That signal change 9600 times in 1 second. That's the meaning of that. Let it be. So this 9600 means 9600 times the signal changes in per second. In 1 second means in per second. Per second we can write by divided by 1 second. Mathematically we can write like this. This is 1 bit. This is 1 second. In mathematical calculations, I can bring this 1 second to this in the numerator. Then I multiply this 1 second to this 1 bit, then I obtain this. Okay, I just gave this 9600 right before 9600. This second, okay, this is a combination of 1 second into 1 bit, right? Okay, so 1 can be multiplied by this, then I get 1 second. So this second I can reduce it to lower unit in any mathematical expressions, calculations, or in physics or in electronics, whatever. Okay, in maths, everybody study maths, I know that. So so let's reduce it to lower unit of time. This is standard unit of time, that's second. Let's reduce it to microsecond. 1 second equal to 10 to the power minus 6 microsecond. So let me write thousands microsecond. I simply put divided by 9600. Here also I simply put divided by 9600. I divide this thousands by 9600. Then I obtain these values. Okay, this microsecond unit, I took it from this. Okay, because this 9600 is just a number of how many times the signal changes. Okay, representing a number of something, how many times the signal changes. There is no unit of number of that must change, number of that must change. There is no unit. So we don't get any unit from there. So I simply took this microsecond unit. So here I put just microsecond unit. So what does it mean? Here I have told before, let's consider sending of 1 bits only. And I also said that this is about sending 1 bits. Okay, in sending 1 bits I get this much of times. But here this is a result of 1 second into 1 bit. Okay, so this is a result of 1 bit into time. Second is time, right? So in sending 1 bit I get this much of times. That means in sending 1 bit I need this much of time. Okay, so after sending 1 bit I need to wait for this much of time, because this much of time is required to send at least 1 bit. So I need to wait for at least this much of time after sending 1 bit. Then I will send 1 bit, I will wait for this much of time, then I will send another bit, then I will wait for this much of time, then I will send another bit. That means the speed at which the bits are sending, the rate at which the bits are sending. Do you get my point? Done. Then let me reduce this time. How? If I make this baud rate value, other value like 115200. There are other values of baud rate like 115200. That is the highest baud rate value that commonly used, but this is more generally used, this value. So I use this values, but we can replace by 115200, then denominator become very high compared to numerator. Then this value when divided by 115200, it will become, here it will become small value, okay, almost half. Then I have to say, for example, it is around 50 microsecond. Then after sending one bit, I have to wait for 50 microsecond. Then I have to send another bit. Then I have to wait 50 microsecond. Then less time I'm waiting. That means the speed of sending, overall speed of sending one bit after another, the time is reduced. Then now it is faster. So this is speed of data transmissions in the UART. So speed is becoming faster. But here I'm using 9600 baud rate value. That's why I got this much of time. That means I have to wait for this much of time after sending one bit, and after that I can send one bit. So this becomes a speed of sending the bit in the UART data transmission process, right? So that's how it is. But that's it. Finish. Now let me say again. 104 is integers portions. So we will store in the UART integers baud rate divisors register, because that is integers portion, right? That's why. And this is fractional portions. So we will multiply, this is multiplication symbol, not underscore. So we will multiply by 64 this fractional portion I have written here, and then add 0.5 to it to get 11 decimals value, because dealing with decimals value is more easier than dealing with all those higher lots of number fractionals value. So we just too often decimals value everybody has to multiply by 64 plus add 0.5 to it. This is a rule. And I will just store this decimals value in the UART fractionals baud rate divisors register. This one, UART fractionals baud rate divisors register, because this decimals value is actually obtained from this fractionals value. This decimals value is just meant to be decimal, so that we don't deal with decimal is more easy to deal with the fractionals value. So that's the reasons I wrote in the code 104 store in the UART integers baud rate divisors register, and 11 store in the fractionals baud rate divisors register. UART. So here I wrote 11 in the 11 is the values of fractionals baud rate divisors register, and 104 as the values of, I store 104 in the integers baud rate divisors register UART. So what does this two line represents? This two line represents the speed at which bit will be flow. Bit means data. Bit or bits will be flow. The speed at which bit will be flow in the UART data transmission process. It will be flow bit by bit. After sending one bit, one has to wait for 104 plus 11 microsecond. Then it can send another bit. Then after waiting for 104 plus 11 microsecond, it can send another bits. Like that, bit by bit. Stream of bit will be flow in the UART data transmission process. Here it is not flowing, but here it is just saying, okay, the time gap to be, the time gap, okay, to be weighted between two consecutive bits when sending. That means it makes, okay, the speed of bit, okay, flowing in the UART data transmission process, as I have explained before. So this is actually the rate at which bit is flowing in the UART data transmission process. This two line represents the rate at which bit will be sending in the UART data transmission process. Okay. So UART 5 is now using CC, the clock registers, and its value is 0. That means to use the system clock. Okay, when things are all zeros, okay, then it means, okay, to use the system clock. This is a clock registers. And then another one. Okay, so what does this line means? 6 in hexadecimal is 0110, 0 in hexadecimal is this. So what does this line says? This line 6 in hexadecimal is this, and 0 in hexadecimal is this. So this line is saying just, again, UART 5, okay, now using LCRS registers, and LCRS registers value is equivalent to 0x0, 60 in hexadecimal is this. So what does this is? Okay, here the bit D3 is a stop bit 2 bit. The name of this D3 bit is stop bit 2, and I didn't set it, I just make it to use its default value 0, and the default value of bit stop bit 2 is to use only one stop bit. Commonly we use two stop bit, but here we are using only one stop bit. Okay, it depends on the device. If the device is, okay, quick in, okay, processing, then we need only one stop bit. This bit D4 and D5, no, D5 and D6, this bit D5 and D6, I set it to 1 1, and setting the bit D5 and D6 1 1 made it to perform a function called an operations called WLAN. That means what LAN? This one, a D5 and D6. When set, and this D5 and D6 when set it to 1 1 of this UART LCRS register, okay, it makes to perform the WLAN functions. The WLAN means in full form is what LAN. Okay, when this D5 and D6 is 1 1, here 1, here 1, D5 and D6, it meant to choose the 8 bit. That means we will use 8 bit in making our data frame. And here this is D3 bit. The D3 bit is called the stop bit 2. And this D3 bit, we use the default value 0. And so the default value of this bit, stop bit 2, is to use one stop bit. So we will use one stop bit in making our data frame. So in overall here, what does this line says? This line says, as we are going to use stop bit 2, default value zeros, it means we will use one stop bit and we will use 8 bit in making our data frame. The first stop bit the start bit will be added by default in making the data frame. Okay. In hexadecimal is this, 0 in hexadecimal is this, 1 in hexadecimal is this. I mean this, okay. 3 in hexadecimal is this, 0 in hexadecimal is this, 1 in hexadecimal is this. So this UART 5 is now using the control register, and its value is equivalent to 0x301. Okay, 301 means just nothing but this bit of the control register. So let's say whatever bit set of this control register, this is the UART enables bit. UART is now enabled, so we can use the UART. This is the D8 bit. The D8 bit is the transmit enables bit. So we have now enabled it by setting it to 1. That means you can now transmit data using the UART data transmission process. This is receive enables bit. So you can now receive data through the UART data transmission process. Let me show you this resistor so that you become more familiar with that resistor. This is the control resistor. I write in the code CTL is full name. You can write also in the code we will write only CTLs, but its full name is UART CTL. Okay. Everybody knows that either by UART CTL or CTL, but usually we prefer writing CTL in the code. Okay, that's it. So let me explain it. Okay, UART CTL. So yeah, UART CTL is 0 bit is UART enabled bit. So I have set it in my code and put it this value as 1. So UART is now enabled, so you can use UART now. This D8 bit, TXE bit, TXE means transmit enable. So now transmit is enabled as you have set in the code by putting its values 1. So you can now transmit data or bit stream or byte through the UART data transmission process. This is the RXE bit, D9 bit. Okay, so this is receive enable bit. RXE means receive enable. So you have now set the receive enable bit, so you can now receive bytes, bit by bits, bit streams, data through the UART data transmission process from other device. Okay, so now we have enabled UART. You can now receive data, transmit data. Okay, so this is about the initializations of UART, and also I have enabled UART in this. Okay, as this bit of the control register bit 0s is UART enable bit, and I have set this bit so UART is now enabled. Okay, I have initialized UART. Now let me initialize this GPIOE or port E. Here let me use other bit. So 0x30. I always use that 0 bit and 1 bit in before I get code, so let me use another bit here. 3 in hexadecimal is 0011 and 0 in hexadecimal is this. Let me explain you something. Okay, this is a pin of this GPIO. Okay, what I'm going to explain. Okay, let's talk about this. The port E or GPIOE. This is the pin of GPIOE or port E. This, what I'm going to explain, is nothing related to this. Okay, it's only related to this, but let me explain this. Okay, with respect to GPIOE or port E written here. Okay, so here this bit, this is D4 bit. Sorry, here this is pin number 5, and this is pin number 6. Okay, of this port E. E has pin 1, 2, 3, 4, 5, 6, 7, 8, right? So GPIOE or port E is same. So this one is pin start from 1, so this will become 5, pin number 5, so this will become pin number 6. Pin start from 1, bit start from 0. Okay, so that's why. So I have chosen pin number 5 and pin number 6 of this port E or GPIOE same. Okay, and why I have chosen only 2 pins. I have chosen only 2 pins. I didn't choose more than 2 pins. I didn't choose less than 2 pins. Why? Because I need only 2 pins for your data transmission process. One for TXT pins and one for RXD pins. Again, this one for TXT pin is the pins through which all the data or bit stream or bit by bits or bytes are transmitted through the UART, from the UART circuitry to the UART data, through the UART data transmission medium to other device. Okay, so that's the reason. And this pin is going to be act as TXT pins, and this pin of this port E of the TIBA microcontrollers will be used as the RXD pins, the pin at which we will receive all the kinds of data or bit stream or byte or bit by bits we will receive through the UART transmissions medium from other device. So that's the reason I need only 2 pins, one for TXT, this one, and one for RXT. Okay, 3 in hexadecimal is this, and 0 in hexadecimal is this. So, I didn't explain this then, so let me explain it, okay? So, this line is saying GBIOE is now using the DEN register, and DEN register value is equivalent to 0x30. Okay? So, what does it means? Okay, this we will put, okay, as a value of the DEN register. And why we put, so that these 2 pins, okay, of this GBIOE or port E is, we are making just a digital, okay? So digital, because everything we are working here is just digital, as we are not using any analog functions here. So because of that reason, okay, its function is only to make it digital. And the function of this is, okay, so your GBIOE is now using AFSL resistor, 32-bit resistor of TIBA microcontroller on Cortex M4 bus microcontroller, and this AFSL resistor is a 32-bit resistor, and this value is equivalent to 0x30. Okay, 3 in hexadecimal is this, and 0 in hexadecimal is this. So what does this AFSL resistor says here? Not, okay, this value is obtained from this. That means this value will also be put in this resistor, okay, from bit 0 to bit 7. Okay, why? Setting only these 2 pins. This AFSL resistor is just same. The 2 pins that of GBIOE, okay, that you have, okay, chosen, make it okay, not remain just simple IO, but make it to functions for, okay, more, okay, other valuable functions like I2C, UART, SPI, timers, and many more. Okay, so that's it. And what AFSL says is, you know, just, okay, make whatever pin you have chosen, okay, for this GBIOE, let it not only remain only as simple I/O, but also make it work for other useful functions like SPI, I2C, UART, timers, etc. Okay. And what does this mean? GBIOE now using AMSAL registers, and its value is equal to 0. This, sometime the pin of the TIBA microcontroller is on Cortex bus microcontroller. This is a very advanced microcontroller. So usually, okay, advanced microcontrollers, their pins are multifunctional. That means their pins can operate more than one functions, like the pins can operate for UART and also for analog to digital conversions. So putting this here, I see AMSCL equal to 0. I'm putting the values of AMSCL resistor because putting the values of AMSCL resistor equals to 0 meant the pins of this TIVA microcontrollers to operate only for UART and not for ADC, analog to digital conversions. So that's the reason I put AMSCL equal to 0. So the pins only work for UART and not for ADC. Yeah. And then another in hexadecimal this, 0 in hexadecimal is this. This 3 in hexadecimal is this, 0 in hexadecimal is this. Here, the GPIOE is now using the port control resistor, and value of port control resistor is 0x30. 3 in hexadecimal is this, and 0 in hexadecimal is this. Here I'm putting the bit I'm setting the bit this is D4 and D5 bits of the port control resistor because I just want to set setting the bit D4 of the port control resistor will makes the bit the pin 5 of this GPIOE to act as this one as DXT pins. DXT pin is the pins where we transmit all kind of data or bit stream or bytes or bit by bits through the UART transmissions mediums to other device. And setting the bit D5, this is D5 bit of the port control resistor, will make the pin D6, the pin 6 of the GPIOE to act as RXT pins. RXT pin is the pins where we receive all kind of data or bit streams or bytes or bit by bits through the UART data transmission process from other device. So because of that, so this is setting up of the pins of GPIOE as UART to be used for UART. So all this above setup takes at least 1 milliseconds delay, so I will just call the delay function which gave me is 1 milliseconds delay when I call only one time. So I will just call the delay functions one time, as this delay functions gives 1 milliseconds delay. So let me write these functions. This is very simple function. This delay function. I'm just taking two variables of integers type, and this is outer for love. Everybody knows, I believe. Even if you don't know, I will just explain it. This is very simple thing. When I learned the code, I know this part. So this is delay functions, and this is just okay the function's name here. Okay, here I have wrote one, that means one time I'm calling. I will pass that one here, and then the values of n will be 1. So here okay, I is 0, and so here I is 0 and I less than 0 is true, the condition is true, and after that I is incremented, okay, to 1. Here the condition is true, so this line will be execute, okay. So this line will be execute, and we'll come to this line, and this line g equal to 0, and 0, okay, j is now 0, so 0 less than 3180, that's true, and j is incremented to 1. But this condition 0 is less than 3180 time is true, so this line will execute, okay. So this line will j is now okay 1, as I incremented j here previously, so 1 less than 3180 time is true, so this line will execute again, and then so it will execute until okay j becomes 3179. But since the j is 0 starting and the starting j is 0, right, so j is so this line is executed 3180 time. In actual, this line execute only one time, okay, because when it was incremented before, but here okay j become okay 1, and 1 okay less than 1, as n value here 1 okay pass to this n as value, so n is now 1. 1 less than 1 is false, so this line stop executing, and after that this one will never execute. So because of that, and 3180, why 3180, we calculate the time of this, we calculate the time, how much time it takes in executing this line, how much time it takes in executing this line, how much time it takes in executing this line, okay. Depending on that, we put this value 3180 time, so that okay this whole okay things takes to tell 1 milliseconds delay, okay, 1 milliseconds. So that's the reason. So we call this, so that this functions give only 1 milliseconds. It takes 1 milliseconds to execute, okay. So I call this function one time, as the functions give 1 milliseconds delay, it will give me only 1 milliseconds. If I call the functions 2 times, it will gives, this function will execute 2 times, so 2 milliseconds I will get. As I need only 1 milliseconds, because it takes all the above process takes at least 1 milliseconds, I will call this delay functions only one time, because I need only 1 milliseconds delay. Here I will in this C I want to receive I'm calling the receive functions, okay, but I haven't explained this receive functions, so let me just explain it, because I have to write this receive function first. Here I need to write the receive function first, because after receiving then I can transfer, transmit or send, okay. Because of that I will write the receive function first. what we are going to receive is of char. Here I'll just take a variable C so that I can store in the C whatever I receive. Well, let me explain it. 1 in hexadecimal is just 0 in hexadecimal is just. Okay, let me explain it. This is very simple. Okay, just listen. Okay, carefully. This line UART, here I'm using UART 5, I think. Here the UART 5 is now using this UART 5 is now using FR register, that means flag register, UART flag register, and this flag register's value is equivalent to 0x10. 1 in hexadecimal is this, and 0 in hexadecimal is this. But what does this line means? This line means only this bit DK4, because this is the only bit that is set. Set means putting its values 1. So, okay. And what does this bit? This bit is the receive flip-flop, receive flip-flop empty flag. Okay. So let me tell you about the receive flip-flop empty flag. So let's see what is receive flip-flop empty flag. So here is the UART FR register, that means the UART flag register. Okay, these are all whatever here is all flag. Okay, so this is the D4 bit receive flip-flop empty flag. Here the receive flip-flop empty flag. The D4 bits receive FIFO empty flag. So let me tell you about this receive FIFO empty flag. The main thing about flag is when it will be set. That's the main thing about any flag, when it will be set. Okay, so let's see when this receive FIFO empty flag will be set. Okay, so let me tell you when it will be set. When a byte has been received from the UART data transmission process, that data or byte, I will say that data will be first placed in the receive buffer. This is spelling is wrong. This should not be the RECEIPED, receive. So whatever data or byte that we receive will be first placed in the receive buffer, ensures a way that the start bit will come first and store in this receive buffer. After the start bit, the ith bit will come, and after the ith bit, the stop bit will come in this receive buffer. As soon as the stop bit came in this receive buffer, the UART circuitry will discard the start bit, and the stop bit will be also discarded, and just only take ith bit data and store that ith bit data in the data register. As soon as only this 8 bits stores in the data register, this receive FIFO empty flag will be set. Let me tell you again, when a byte or data has been received from the UART data transmission process, it will be first placed in the receive buffer in such a way that the start bit will come first, and after the start bit the ith bit will come, and after the ith bit the stop bit will come, and then store in this receive buffer. First the start bit, then the ith bit, then the stop bit. As soon as the stop bit is received in this receive buffer, the UART circuitry will discard the start bit and will also discard the stop bit, and only the ith bit data will be placed in the data register. As soon as ith bit data is stored in the data register, this ith bit will be stored in the data register. After that, this receive FIFO empty flag will be set. Okay, by putting its value 0. Remember, by putting its value 0. Okay, so this UART 5 is now using the FR register flag UART flag register or FR register, and this FR register's value is equals to 0x10, and 1 in hexadecimal is this, and 0 in hexadecimal is this. But this line only mean this, and this is the receive FIFO empty flag. Okay, so this whole line means only this bit receive FIFO empty flag. This receive FIFO empty flag is now not equals to 0. Okay, but it will be 0 after some time, because here there is something while says wait for some times. That means now it is not equals to 0, this receive FIFO empty flag, but it will be 0 after some time. When it is 0, this receive FIFO empty flag will be set. Okay, this while says it is not 0, but it will be 0 after some time. After some time, that means we are waiting for some time, and what we are waiting is, as you know, the data receive will be stored in the receive buffer in such a way that start bit will come first, and after the start bit ith bit data will come, and after the ith bit data the stop bit will come. Okay, and comments in the receive buffer. As soon as the stop bit is came in the receive buffer, this UART circuitry will discard the start bit and the stop bit and only kept this ith bit in the data register. This takes some time, so that's the reason we are waiting for some time. And when we get data in the data register, that means when this ith bit is get in the data register, stored in the data register, then this receive FIFO empty flag will be set by putting its value 0. So this one is not equals to 0, but it will be 0 when the ith bit data is kept in the data register. So here the flag will be set after some time, and when the flag will be set, it means that the ith bit data is stored in the data register. That means the data is stored in the data register. Finally we get the data. Okay, so we will write UART5 implies GR. That means we get the data in the data register. Okay, as the flag is set here, that means ith bit data is in the data register. So we will write here the ith bit data. That means the data is in the data register. That means UART is now using the data register. That means the data is in the data register. That means we are getting data. Okay, so here it is saying the flag is set. That means we get the data in the data register. So I will store that data in the variable C that I wrote here, and I'll just return that data stored in the C. Okay, when we call in the main functions, here I call that receive functions, and I get it returns a data, and that data I store in this variable C. Okay, and after that I want to transmit this data again to another device. So let me write the functions of transmit. This one is the data we are going to pass, and then we will transmit. This is the name of the functions. This is same as before. Here I'm only using the transmit flag 2 in hexadecimal states and 0 in hexadecimal states. Okay, so let me explain this function. This function is very easy, but listen carefully. Okay, here it is just saying UART 5 is now using the FR register, that flag register, that UART flag register, and its value is equivalent to 0x20, 2 in hexadecimal. This 2 in hexadecimal is this, and 0 in hexadecimal is this. And what does this line says? This line only means this bit D5, because only this bit D5 is set. So because of that, this line means only bit D5. Then what does it mean? This line only mean this, and this only mean this. Then this whole line only mean this, and this is transmitting FIFO full flag. Okay, and this bit is D5 bit is transmitting FIFO full flag. So let me tell you about transmitting FIFO full flag. So this bit D5 is the transmitting FIFO full flag of this. This is transmitting FIFO full flag is the D5 bits of the UART FR register, UART flag register. Okay, this is the transmitting FIFO full flag, the D5 bits of this UART flag register. So let me tell you about transmitting FIFO full flag. When you want to transmit a byte of data, you first place that byte in the data register, and after that byte is shifted to the FIFO buffer or in the buffer. Okay, after that, this transmit FIFO full flag will be set by putting its value 0. Lower means 0. After this flag is set, the byte you have kept in this buffer will be framed between the start and stop bit and transmit by the TXT pins. Okay, TXT pins is the pins where we transmit all kind of data or bit streams or byte bit by bit. Okay, using the UART data transmission process to other device. So that's it. Let me explain you again. When you want to transmit a data through the UART data transmission process. You first place that byte in the data register, and after that data is shifted to the FIFO buffer. After this transmit FIFO full flag will be set by putting its value 0. Okay, 0. When this transmit FIFO full flag is set, the byte you have put in the buffer will be framed between the start and stop bit and will be transmitted by the TXT pin. TXT pin is the pins where we transmit all kind of data or bit stream or byte or bit by bits through the UART data transmission process. Okay, so let's come to our code. So here UART 5 is now using the FR register, the flag register, the UART flag register, the UART FR register, and this FR register values is equivalent to 0x20, 2 in hexadecimal is this, and 0 in hexadecimal is this. But this line says only this bit, and this bit is the transmitting full flag, transmitting FIFO full flag. Okay, so this line represents only this line, and this line means only this line, and so this line means only this bit. This bit is transmitting FIFO full flags. This bit is transmitting FIFO full flags. So this transmitting FIFO full flag, so this one is transmitting, so this line represents transmitting FIFO full flag. This transmitting FIFO full flag is now not equal to 0. But this while says wait for some time, then it will be 0. When it is 0, this transmitting FIFO full flag will be set. Right? This will be set when its value is equal to 0, as I mentioned before, that transmitting FIFO full flag will be set when is lower. Lower means when its value is 0. And here this line represents, as I told, the transmitting FIFO full flag, and this is not equal to 0. But here the while says it will be 0 after some time. After some time. That means it is not 0, it will be 0 after some time. That means we are waiting for something. We are waiting for something, and what we are waiting is the data to be placed in the data register and that data to be shifted in the FIFO buffer. That's what we are waiting. It takes some time, so we need to wait. So because of that, we are waiting. When the waiting is over, that means when the data is in the buffer, this will be equal to 0, and thus transmitting FIFO full flag will be set by putting its value equals to 0. At that time, this will be equal to 0. When it is equal to 0, that means the flag is set. This transmitting FIFO full flag will be set. Then data will be transmitted, right? So we will write here so what does it mean? This line says C is the value, the data we pass here, and so this data we have to store in the data register. As I mentioned always, the byte you want to transfer should be placed in the data register. The byte you want to transfer should be placed in the data register. So that is the byte, that is the data we pass to be transmitted. So this data we place in the DR register, data register. And what does this line means? This line means now we are using UART 5 is now using the DR register. It can use many other register, but this line says now UART 5 is now using DR register. Why DR register? Only, not other register. Because the DR register is a register where data, whatever you have to transmit, has to be placed in this data register. That means all the data put in this data register will be transmitting. That means data will be transmitting. That means data is transmitting. Okay, so that's the reason we are writing here UART 5 is now using the DR register. That means data, whatever we have put in the DR register, the C. Now as DR register says that whatever data you want to put will be placed in the data register. Whatever data you will be transmitting or will be used in transmitting will be put in the DR register. That means every data you will put in the DR register will be transmitting. That means it is transmitting. Okay, so here it says the transmitting FIFO full flag is set. So here this line says data is transmitting. So here we receive data using these receive functions, and I store that data here, and we will transmit calling that your transmit functions. And I call this transmit functions and pass this data to this here, because this function pass the data. Right, here suppose the data we get is A. Okay, let's for example make it a very simple one so that we can understand it very clearly. Suppose the data we receive is A. A has ASCII values of 41. Okay, 4 in hexadecimal is this, and 1 in hexadecimal is this. So this is a binary value of this A. So this will be a frame between the start bit here and the stop bit after the MSB. So this bit, start bit will be received first in the receive buffer, and after how many minutes? What we set the rate of data flow or speed of data flow is 104 plus 11 microsecond rate. So after receiving the start bit, we will wait for 104 plus 11 microsecond, and then this LSB will come first. In the UART, you should know in the bit stream LSB is sent first and LSB is received first. Okay, send first means it will receive first, right? Which is contradict to I2C. In I2C, MSB is sent first, but in UART, but in I2C, MSB is sent first, but UART, LSB is sent first. Okay, so start bit will come, and after that I have to wait for 104 plus 11 microsecond because of this rate of data flow we set here. We told that 104 plus 11 microsecond we have to wait between its consecutive bit sending. So after that LSB will come. After LSB I have to wait for 104 plus 11 microsecond, and after that this bit will come like that. Okay, all the bits will come, and this is same for transmitting also. In the transmitting, it is frame between the start and stop bit. The same bit will be frame between the start and stop bit. First the start bit will send, and then we have to wait for 104 plus 11 microsecond, and then after that the LSB has to send first, right? So that's the way we receive and then transmit from other, we receive from other device and then we transmit to another device through this process in UART. Thank you all for the session.